We are the Group 4 and we are tasked to discuss the chemistry for engineering materials, specifically the basic concept of crystal structure and fuels.
Good day, everyone. I am Christine Joyo Fabian. I will discuss the types of solids. There are two general classification of solids, which is the amorphous and crystalline. Amorphous with no pattern to the arrangement of particles. Their melting point is over a wide range of temperatures. They just get softer and softer when heated. For example, glass, plastic, and wax. Crystalline, it is well-ordered, different arrangement of atoms. Crystals have a repeated structure and a melting point at a very narrow range of temperature. Example of metals, H2O, diamond, and table salt. Crystalline also has four types of solids: the molecular, which formed from molecules; network covalent, formed from atoms; ionic, formed from ions; and lastly is the metallic, formed from metal atoms. So let me discuss further about these four types.
What is crystal structure? A crystal structure is made of atoms. A crystal lattice is made of points. A crystal system is a set of axes. In other words, the structure is an ordered array of atoms, ions, or molecules. Crystal structure is obtained by attaching atoms, group of atoms, or molecules. This structure occurs from the intrinsic nature of the constituent particles to produce symmetric patterns. A unit cell is the building block of the crystal structure, and it also explains in detail the entire crystal structure and its symmetry with the atom position along with its principal axis. The length, edges, or principal axis, and the angle between the unit cells are called lattice constants or lattice parameters. Crystals use X-rays, which excite signals from the atom. The signals given by these atoms have different strengths, and they usually depend upon the electron density distribution in closed shells. The signals released by the atoms varies. Lighter the atoms, weaker is their signal. The 7 crystal systems. Cubic crystal system. Triclinic crystal system. Tetragonal crystal system. Monoclinic crystal system. Trigonal crystal system. Orthorhombic crystal system. Hexagonal crystal system.
Good day. Let's discuss about laws of crystallography. There are three laws of crystallography: the law of constancy of interfacial angles, rational indices, constancy of symmetry. The law of the constancy of interfacial angles, or the first law of the crystallography, states that the angles between the crystal faces of a given species are constant, whatever the lateral extension of these faces and the origin of the crystal and are characteristic of the species. Let's move to the second law of crystallography, the law of rational indices. The law of rational indices states that the intercepts OP, OQ, OR of the natural faces of a crystal formed with the unit cell axes A, B, and C are inversely proportional to prime integers h, k, and l. They are called the Miller indices of the face. Now, let's move to the third law of crystallography, the law of constancy of symmetry. According to this law, all crystals of a substance has the same elements of a symmetry: plane of symmetry, axis of symmetry, and center of symmetry. Plane of symmetry. A crystal is supposed to have a plane of symmetry. One imaginary plane passing through the center of crystal can divide into two parts which are mirror image to each other. Axis of symmetry. An axis of symmetry represents a line about which the crystal may be rotated so that it represents the same appearance more than one during the complete revolution. Center of symmetry. A crystal is supposed to have center of symmetry if every face has an identical face at an equal distance on the opposite side of this corner. Let's talk about diffraction of X-ray by crystal. X-ray diffraction is a phenomenon in which of a crystal, by virtue of their uniform spacing, cause an interference pattern of the waves present in an incident beam of X-ray. The atomic planes of the crystal act on the X-ray in exactly the same manner as does a uniformly ruled grating on a beam of light. For electronic magnetic radiation to be diffracted, the spacing in the grating should be the same order as the wavelength. In crystals, the typical interatomic spacing to -3 so the suitable radiation is X-ray. Hence, X-rays can be used for the study of crystal structures. So, a beam of X-ray directed at a crystal interacts with the electrons of the atoms in a crystal. The electrons oscillate under the influence of the incoming X-ray and become secondary source of EM radiation. The secondary radiation is in all about direction. The waves emitted by the electrons have the same frequency as the incoming X-ray or coherent. The emission will undergo constructive-destructive interference.
Hi, this is Desiree, and I will going to discuss the Bragg's Law. First, what is Bragg's Law? Bragg's Law was introduced by the father and son William Henry Bragg and his son William Lawrence Bragg. The Bragg's Law is useful for measuring the wavelength and for determining the lattice spacing of crystal. Let's illustrate. Using the Bragg's equation, and wavelength equals 2d sin theta. This is the layer of atoms in crystal. The arrow represents the light that is bouncing off through them. The light is known the wavelength. D is the distance between the layers of atom. Theta is the angle that the light hits the layer. Let's have a solving problem sample using the Bragg's equation. This is the problem. If the wavelength striking a crystal at 38.3 degree angle and has a wavelength of 1.54, what is the distance between the two layers? Let's assume n is equals to 1. Note, you need your calculator to determine the sin of this angle. Now, let's use the Bragg's equation. N wavelength equals 2d sin theta. Then after that, we will substitute the given, which are n is equals to 1, wavelength is equals to 1.54, d is missing, and the theta is 38.3 degree. D is the missing here. So, let's rearrange the equation to D is equals to N wavelength over 2 sin theta. So, the equation will look like this. Use a calculator and input the givens. So, the answer is this. So get only 2 decimal places, though the answer will be 1.36. Now, let's discuss allotropes of carbon. Allotrope is an element that has more than one physical form. Means it has a similar chemical property but different in physical form. To elaborate this meaning, let's take a simple example. Water and ice. It is the same H2O but in different physical form. Every element can be allotropes, but here we will focus on carbon. There are two kinds of carbon, the free state and the combine. But free state is the only allotropes of carbon because it does not require to be combined with other chemical properties to form a new physical feature. Free state has two forms, the amorphous and the crystalline. Amorphous form means the carbon atoms have an order in proper arrangement, while crystalline form means the carbon atoms are properly arranged. So, crystalline form is the only allotropes of carbon here. Crystalline has three forms too. These are diamond, graphite, and fullerene. But I will only focus to discuss the diamond and the graphite. Diamond is formed under the Earth's surface due to very high temperature and pressure. In diamond, each C atom is connected to 4 C atom that is known as the tetrahedral structure, which makes the hardest allotropes of carbon, and it gives a high melting point. Since all electrons is bonded, it makes a bad conductor of electricity. Then, let's move on to graphite. It is dark and dull in appearance. Graphite, each C atoms is connected to 3 C atoms that form a sheet. It is a good lubricant. For the same reason, it is used to make a pencil leads. But the melting point is still very high, and it is a good conductor of electricity.
This time, we are going to learn about the structure of buckyballs, also known as Buckminster fullerenes, graphens, and nanotubes. And the importance of area of science is called nanoscience. You may already familiar with diamonds and graphites as two allotropes of carbon. Allotropes are structurally different forms of an element. The graphites exist as sheets of carbon atoms arranged in hexagonal rings. Fullerenes are carbon-based molecules with a hollow cage-like structure. Robert Karl, Harold Kroto, and Richard Smalley discovered the most common fullerenes in 1985. Buckminster fullerenes consists of molecules containing 60 carbon atoms joined together forming a hollow sphere. There is an alternative arrangement of hexagon and pentagon much like that seen in a football. Why do you think the space inside the fullerenes is so important? The answer is the space is big enough for atoms and molecules to fit inside already. The scientists are utilizing this cage radioactive metal atoms and drugs in one potential drugs therapy. Balls containing cancerous drugs are coated with a chemical that causes them to gather around cancerous cells once, where they deliver their drugs without harming healthy cells. Graphene is very similar to a graphite except there are no intermolecular forces holding the hexagonal arrangement of the carbon atoms together. It has a two-dimensional structure. It has some very special properties which make it materials for the future despite being one atom thick. Is it incredible strong and graphenes can conduct electricity. Fullerenes hold a special importance in nanoscience, a relative new area of science which involves the study of nanoparticles. Nanoparticles are tiny particles made up of only a few hundred atoms. They can measure between 1 nanometer and 100 nanometer across. Nanometer is a billionth of a meter. To illustrate how small this is, a human hair is about 100,000 nanometers in diameter. Graphene particles can be joined together to make nanotubes. These nanotubes have massive surface areas compared to their volume, and this makes them excellent catalysts. You may recall that a chemical reaction takes place at the surface of a catalyst, and so having more surface enable catalysts to work more efficiently. Nanotubes are the strongest, stiffest materials ever discovered. Often they are used to reinforce tennis racket made out of a graphite. All these fullerene structures are revolutionary in the developing field of nanoscience.
Nanotube mentioned here can be implicated in the development of a self-cleaning coating in ovens or in a window, new types of a computer processing very strong and light building materials, and this following could be used sensors to detect substance in a fine amount or to deliver drugs to a specific site in the body. To cut the long story short, there are three key nanoparticles: the Buckminster's, Fluorines, Graphens, and nanotubes. These nanoparticles have a wide range of potential use for the future.
Non-conventional source of energy. These are the type of non-conventional source of energy: solar energy, wind energy, hydro energy, geothermal energy, biofuel energy, and biogas energy. Solar energy. Harnessed by converting solar energy directly into electrical energy using solar cells. Inspired by the photosynthesis process in plants. Wind energy. Harnessed by converting kinetic energy of the wind directly into electrical energy by the help of windmills. As wind increases, power output also increases. Wind speed is usually higher in higher altitude. Tidal energy. Converts the energy of tides into electricity, helpful in areas where sea experiences waves and tides. Biomass energy. The organic matter that originates from plants, animals, wood, sewage. Substances are directly burned to produce heat energy, which is then used to generate electricity. Geothermal energy. Heat energy that we can get from hot rocks present in the earth crust. Geothermal wells releases greenhouse gases trapped within the earth, but these emissions are much lower per energy unit than the fossil fuels. What are the needs for non-conventional energy sources? With increasing population, the energy consumption as well as the demand has increased tremendously. Nature has a very limited supply of the conventional sources of energy. In order to meet the increasing demand, renewable sources of energy is required. What are the advantages of non-conventional energy sources? They are renewable in nature, cause little or no population as compared as the conventional sources of energy, low maintenance costs, cost savings option in the long run. And what are the disadvantages of non-conventional energy? Initial setup cost is higher. Energy cannot be extracted 24/7 year-round because some days will be windier than the other. On some days, sun will shine brighter. Energy has to be stored. Geographic locations can be challenging. That's all for non-conventional sources of energy.
Biomass energy is generated or produced by living living organisms. Biomass energy, people have used biomass energy from living things since earliest or cavemen. First made wood fires for cooking, keeping warm. Today, biomass is used to fuel electric generators and other machinery. Biomass is organic, meaning it is made of material that comes from the living organism, such as plants and animals. Some example of biomass like fuels, firewoods, crops, manure, and some garbage. Biomass can use fuels, power production, products that would otherwise be made from fossil fuel. Biogas combustion reaction. It is produced by anaerobic fermentation, biodegradable materials. The utilization of biogas, wide form process of combustion. Combustion reaction between methane and O2, then carried the combustion chamber to produce CO2, H2O, N2, and excess O2, bring heat from combustion reaction, and exit from combustion chamber at higher temperature. Biogas resulted from anaerobic digestion of organic compounds. Have various methane content depend on the type of the degraded material. The methane content of biogas is range between 40 to 80% that influence that heating value and combustion characteristic of that biogas.
What is solar energy? Solar energy is the radiation from the sun capable of producing heat, causing chemical reaction, or generating electricity. The total amount of solar energy received on Earth is vastly more than the world's current and anticipated energy requirements. If suitably harnessed, solar energy has the potential to satisfy all future energy. Why is solar energy important? Solar energy is important because it creates pure and clean renewable power from the sun, a perfect alternative to fossil fuels such as natural gas and coal. It also reduces carbon footprint and greenhouse gases worldwide. Solar energy has many benefits to us, such like producing a clean and renewable energy, reducing electricity bills, and many more.